All right, so we're going to start off this next section talking about ionic bonds, because we're going to be talking about the different types of chemical bonds to hold atoms together into compounds and molecules. So remember from the last video that ions are atoms who have either gained or lost electrons to be able to create that full valence shell, that full outer shell with paired electrons. And so ionic bonds are bonds that are created when you get two ions of opposite charges together. So that's all an ionic bond is. It's the electrical force of attraction between oppositely charged ions. So it's just like when we talked about like electricity, positive and negative charges for static electricity are attracted. Positive and negatively charged electrons are positively and negatively charged ions are attracted to each other. So we saw when we created ions, in the examples, we created a sodium ion, a positive ion, +1, and we created a fluorine ion, which was -1. So these guys have actually equal attractions, so they are going to be attracted equally. So we've got the +1, we've got the -1, and so one of each will be an equal attraction to make the compound. Now, if we were looking at something different, instead of sodium, let's say we had calcium. Remember that one I showed you is a +2. If we had calcium, we'd actually need two of these fluorines in order to make the compound, because you need two negative charges to be attracted to balance out the calcium. So I'm going to show you a couple of examples of these guys. So sodium chloride or table salt is actually a very common ionic bond that you would know. It's made up of sodium and chlorine, so same thing. So sodium has that +1, chlorine has the -1. It's in the same group as fluoride, and so it's going to have equal attraction. And if you look at table salt closely underneath a microscope or even just a hand lens, so you can actually try this with the hand lens that you have in your kits, you'll see that it actually makes a structure. It makes cubes. In fact, this is a common thing we see with ionic compounds, that the ions will arrange themselves into very specific structures because of their attraction. Another example of this would be what you're seeing here, aluminum oxide. So aluminum oxide, it's 2 aluminums to 3 oxygens. So it is an ionic bond. So these guys come together in this very specific structure. And aluminum oxide is actually what creates rubies and sapphires. So both rubies and sapphires are made out of aluminum oxide. What makes the difference in the color are the impurities. So there are other elements that have been mixed in among the aluminum oxide to create the colors that we see with rubies and sapphires. But they both have this crystalline structure that's very similar, and it's because of the building of the aluminum oxide with this same structure over and over. So ionic bonds, these guys are crystals. Most of the ionic compounds that you're going to be familiar with are salts. So you've got things like table salt, calcium chloride, that's the one that's commonly found in sidewalk salt. And most of the ionic bonds can be dissolved by some sort of solvent that's also got a charge to it. We'll see a little bit later, we're going to talk about polar bonds. They are bonds that create a slight charge in a molecule. And so, for example, you know that salt can be dissolved by water, and that is because water has a slight charge to it, and so it's attracted to these ions. All right, the next group of bonds are metallic bonds. So metallic bonds are interesting because the way the bonds work is that the outer electrons in metal atoms are weakly held by those atoms. So we talked about this already when we talked about things like electricity and heat. That's actually how they are good at conducting electricity and heat. But for a metallic bond, this works as creating this electronic fluid that the metal ions are floating in. And so you can see down here, this is just a generic picture of how this is working. So we've got the metal ions. They're ions because they've lost those electrons that are just floating around. And so you can see that the metal ions are just kind of floating around in this electronic fluid made up of these electrons that are kind of holding those metal ions together. And again, this is what gives them those properties that we were talking about before when we talked about heat and electricity, of allowing them to conduct heat and electricity, making them very malleable and ductile. It's because they're just kind of in a fluid of electrons. This also is what allows us to mix metals into alloys. You've probably heard of alloys before, things like brass and bronze. They are not true pure metal. They are a mix of metals, but making those mixtures, steel's another one, making those mixtures can make the metals stronger or give them different properties of color, conduction, and so forth. I've got the Sacagawea dollar here because a lot of people think that the Sacagawea dollar is gold, but it's actually not gold. This dollar coin actually is made with copper, zinc, manganese, and nickel. So it's those four metals mixed together that give it that gold color. And then the interior is copper. So that way it can have similar properties to a Susan B. Anthony dollar. It can be spent, for example, in like vending machines and so forth, and still have the magnetic properties of a dollar coin, but it has that different look to it. It has that gold color. Another alloy that if you do jewelry work you might be familiar with is white gold. Most people don't realize white gold actually is part gold, but what changes it from the gold color to the white gold color is palladium. So it's got another metal mixed into it to alter the color of it. It still has the properties of gold, but it has that different color to it. Don't have much else to say on metallic bonds, but that's how these guys work. That's because they've got these free electrons, it allows us to easily mix those different metals together and change those properties. All right, the big group that we're going to talk about are the covalent bonds. And this is because most of the stuff that you know, if it's not a metal, is probably bonded by a covalent bond. So covalent bonds are different from ionic bonds and metallic bonds. So ionic bonds made between ions, opposite charged atoms. Metallic bonds, it's those metal ions floating around in their electron pool. Covalent bonds happen when atoms share their electrons to complete that outer shell. So to get that outer shell of 8, or in hydrogen's case 2. So you can see here we've got a fluorine pair. So fluorine often is found in like ionic compounds, but we can also have fluorine as a molecule. And so if fluorine is going to be formed into just fluorine, these two atoms are going to share that single electron that they each have, and they'll get bonded together in a covalent bond, and they'll then have that set that they need to make 8 on the outside of each, and they'll have a shared pair. This is a very, very strong bond. So thing is that once the bond is formed, they don't want to give up their filled valence shell. They have it, they're stable, they're steady atom, they have their 8. It takes a lot of energy to break a covalent bond. It doesn't take very much energy for us to break an ionic bond. I mean, think about it. You can dissolve salt in water. Now, it does take a little bit more to break something like aluminum oxide. You can't dissolve a ruby in water, but that has to do with the makeup of how those ions work. And same thing, you can't really break apart metal with something like water, but you can actually, use energy to mold and so forth with it. But to break individual bonds of covalent bonds, it takes a large amount of energy. And it's just because these guys are sharing those electrons and they don't want to give up that stable state. So a little more on these covalent bonds. The number of covalent bonds that an atom can form is equal to its number of unpaired valence electrons. So fluorine, it can only make one covalent bond because it just has that one unpaired electron. Same with anybody else in its family. Oxygen, on the other hand, oxygen has 2 unpaired electrons. So it can make 2 covalent bonds. And that's actually what it does when it makes water. So it's going to bond one of those electrons to a single electron with a hydrogen atom on each of its unpaired electrons. So before, you've got just the 3 of these atoms by themselves, but once those covalent bonds are put together, you've got a hydrogen sharing 1 electron with the oxygen, and then the other one on the other side. Now, because of the location of those unpaired electrons, you can see that the hydrogens end up on one side of the oxygen. And we'll see in a little bit why that is important. Now, oxygen's not the only one that does this. A lot of elements on that right-hand side of the table will make covalent bonds. Those are those ones that are kind of in those in-between colors. I said those ones that the table in the last video showed were like +3, -4, -3, -2, that have that kind of in-between color for making ionic bonds, or being made into ions, I'm sorry. They tend to do covalent bonds because it's more efficient, basically, for them to make these covalent bonds rather than trying to give up or get those electrons they need, because they're in that in-between number. So let's take a look at who else makes covalent bonds. So another element that you would know pretty well, hopefully, is nitrogen. This is one that we find in humans and other living organisms. And nitrogen has 3 unpaired electrons. So oxygen is in the family right next to fluorine. Nitrogen's 1 column over. And so it's got 3 unpaired electrons, so it can make up to 3 covalent bonds. The molecule you're seeing here is ammonia, and so it will make those covalent bonds. It has 1 non-bonding pair. Those guys are perfectly happy by themselves, but everybody else is going to bond together, and so you'll get the ammonia with those 3 hydrogens. Carbon is another one. So we saw before, carbon has 4 unpaired electrons, and all of the other members of its family have 4 as well. And so any member of that family is going to be able to make up to 4 covalent bonds. And so in this case, since it's bonding with hydrogen, you're going to get methane, which is a common molecule in natural gas. So if you have natural gas in your home, that is what you're burning, is going to be this molecule right here, which is why we get such a large amount of energy out of it, because when you ignite it, you are separating the bonds here and getting the energy out of that. Now, the other thing with these bonds is I said they can make up to 4 individual bonds. They're still going to make 4 bonds, for example, with carbon, or up to 3 bonds with nitrogen, but they don't have to make them with all other atoms. So let's take a look at these guys. So for example, oxygen, we can make an oxygen molecule. We know that because that's what we breathe. So we can make multiple covalent bonds. And so here you've got oxygen. They're going to share both of their unpaired electrons with each other so that they've got the ones that they need. So they do each have the 8, right? Because this guy has 4. And then with these ones shared, it will have 8. Same on this side, 4. And sharing these, it has 8. So this molecule is stable with both atoms, and so it has a double bond. And so when we draw bonds, and very often you'll see molecules where they don't put the little dots for the electrons. Instead, we'll just draw the lines. A single line is 1 bond, a double line is 2 bonds, and a triple line, like this one over here, is 3 bonds. And the lines are representative of covalent bonds. So straight, solid lines are going to be showing you covalent bonds. And so you can see here for carbon dioxide is going to do the same thing. Carbon has 4. It needs more, so it's going to share 1 set with oxygen so that oxygen's got its 8 on each side. And then, because it's sharing on both sides, carbon actually has all 8 that it needs. So carbon actually is interesting. We'll see this when we get later into other videos about organic molecules, because it is kind of an ultimate building block of molecules since it can do up to 4 bonds. But I just want to show you one material that you probably are familiar with that is unusual in the fact that carbon likes to bond with itself a lot. And so what you're seeing here is the inner structure of the material diamond. And so diamonds are pretty much all carbon. There are some hydrogen ion or atoms, so that's what you're seeing here. But the carbon in a diamond is arranged in a very specific shape. You can see that it's arranged in these hexagonal shapes. So when they bond with single covalent bonds between each other, but they bond in this very specific shape. And this is what makes diamonds that very, very tough material, one of the toughest materials on the planet, because they're put into this same shape. On the other hand, graphite, which is the carbon that's found in things like pencils, especially good quality drawing pencils, which is not what I just showed you, that's also carbon. But the carbon atoms are not arranged in this very strict pattern. And so that's what makes graphite so very, very soft. All right, so that's the end of the introduction on bonds. The next video is going to talk about bond polarity. So it's still going to be talking about things like covalent bonds and a few other topics related to bonds.